Okay, we seem to have reached a critical mass, so we'll get going. Welcome, everybody. My name is Matthew Newstaden. I am the Market Development Manager for Cannabis, Environmental, Food and Beverage Markets here at SCIEX. That means I get to spend a lot of time talking with all of our customers and thinking daily about PFAS testing, which is what we're all here to talk about. This is a 5-part webinar series that we've put together that covers all the areas of PFAS quantitation and screening that you might be interested in. This is a joint webinar series between ourselves at SCIEX and our partners at Phenomenex. And in this first session, we'll be talking about how to avoid PFAS in your testing workflow. These compounds are everywhere, and our speakers today are going to have some great knowledge to impart on how you can avoid them in your lab and in your processing workflows. So a couple housekeeping items before we jump into the actual talk. This session is being recorded, and there is an option at the bottom of your little Zoom window there to submit questions as the talk is going on. And we will then answer those questions in the live Q&A session at the completion of our speakers' presentations. So with that, I'd like to introduce you to our 2 speakers today. We have Karl Oetjen, who's a senior scientist in technical marketing here at SCIEX. Karl did his Ph.D. at the Colorado School of Mines in hydrologic science and engineering, in the lab of Dr. Chris Higgins, which is a sort of a notable name in the PFAS world. And his dissertation focused on non-target characterization of complex surfactant mixtures. So really interesting environmental work, and that included aqueous film-forming foams, which are a known source of PFAS in the environment. Our second speaker is Sam Lodge, who's the Business Development Manager for the environmental market at Phenomenex. Sam's been with Phenomenex for 28 years in various positions, and over the past 4, he's been doing extensive work with commercial and government labs in the development and support of PFAS analytical methods. This includes the stacked tubes and pass-through GCB cartridges that can help commercial labs to increase productivity and reduce costs. So with that, we're going to get into the talks. I do have some polling questions that I'd like to launch. If you could just take a minute and answer those, I'd appreciate it. There is 3 questions there, and as you answer them, if you just scroll down in that polling window, you should be able to get through all 3 questions. So we'll let that run. With that, I'm going to go off camera. I'll see you at the end. Please do submit your questions as we go through the talk, and I will see you at the end during the live Q&A. Karl, I'm ready to pass it over to you.
Great, thanks, Matt. Thanks everybody for joining today. So as Matt said, we're going to be talking about the first part of our PFAS analysis, so really diving into some of the sample prep and also contamination issues and how to avoid them. But before we do that, let's just talk a little bit about the background of PFAS. So in 2001, there were 2 notable studies looking at just a subset of PFAS compounds, specifically PFAS and PFOA as well. And they kind of focused on 2 different things. One looked at a more wildlife global approach. So they're looking at PFAS across the globe. And what they found was essentially there was PFAS specifically in all over the globe, in different mammals, reptiles. So for example, in Antarctica, in penguins and seals. And Antarctica typically isn't a place we would think of it being a PFAS production hub. So really it was highlighting that, yeah, this is a global problem. It's not just limited to, say, the United States or just in industrial areas. The second, by Hansen et al., looked at it in human serum in the United States. And what they essentially found was, yeah, it's in our blood. So we know that is not only an environmental problem globally, but it's also a human issue as well. And ewg.org puts out this really awesome interactive map that shows contaminated sites, whether those be a drinking water site or a military site or some other type of site, where you can go ahead and enter in your address. And I think what you'll probably find is that there's a contamination site probably a little bit closer than you would have hoped to maybe where you live or work. But overall, what we see just domestically is there are nearly 3,000 reported sites where we had some sort of PFAS contamination. And this was in August 2001, or 2021, sorry. I'd imagine now that we're pretty well into 2022, this number is probably a little bit higher. But after this, I encourage you, if you haven't already, go ahead and check it out. It can be really interesting when you start looking at how it affects you and the community that you actually live in. So we know it's an issue, but where is it coming from? And the answer essentially is a lot of different places. There are many different places that it's coming from. When I was doing my PhD work, I was working in a lab that obviously analyzed PFAS. And I would always make a joke to my PI, which he did not find very funny, that because we had these really nice long lab benches, that I was going to bring in my skis to wax my skis, because in my tiny apartment, there just wasn't enough room. And the reason he didn't think that was funny is because typically ski wax uses fluorinated chemicals, and he didn't really want those in the lab. But it's an interesting thing to think about, right? So just on the ski slope, my jacket that I'm wearing that's waterproof, my snow pants, all contained PFAS compounds that made them water repellent, all the way down to my skis. So it's not just one source. There are many different sources. If you think about the sandwich that maybe you ate for lunch, that wrapper likely contains some sort of non-stick properties, which may or may not be PFAS compounds, all the way up to what I did a lot of research on, which would be the firefighting foams, which are used for pretty intense hydrocarbon fires, usually where water wouldn't be sufficient. But the moral of the story is PFAS does a really good job at what it was designed to do. So it has a lot of different applications, and because of that, it affects our life in a lot of different ways. So I'm assuming most of us who are listening are probably from a science background. But what if we think of the, exclude ourselves, or not exclude ourselves, but also include the greater community who also is interested in PFAS? And what we see is, although those two papers came out in 2001, if we look at the normalized Google searches just for PFAS, we really see this big uptick in January of 2018, where more and more people started to search PFAS. And what they're searching might be PFAS in water. As we all probably remember, there are a few major contaminated sites that hit the news around that time. Or they might just be searching, what is PFAS? So it's not just our community that's interested, but it's the greater community as a whole. And I think most of you, or at least some of you, were pretty curious like me, what is that giant spike that occurred not too long ago? So I did a little digging, and it actually corresponds to when John Oliver did a little segment on his late night show, causing that massive spike. So what about not just talking not just about the United States, but let's kind of expand this worldwide. What regions of folks are interested? We see the Americas, of course, in Europe, Australia, parts of South America, but even in Asia, it's becoming a more searched topic. So that's kind of telling me that globally, this is an important issue, and more people are becoming aware of it, not just in the scientific community, but in our community as a whole. And if we look at just the United States, like take a more domestic approach to it, we see areas like Michigan, which have had some issues, have really high search rates, and it's probably because it's starting to affect their life and their community, and they're starting to ask this question: what even is this? What is PFAS? I've heard it, but what is it? So with that, what we're going to really talk about today would be the sample prep portion. So Sam is really our sample prep expert, or one of our sample prep experts, and he's going to kind of dive into some of the approaches that you can use for different matrices, because there are a ton of different matrices. And I will really be talking about the HPLC system, and not so much chromatography, but how to get your HPLC system ready for PFAS analysis, and what are the main sources of contamination, things to watch out for when you're doing this type of work. And with that, I'll go ahead and hand this off to Sam.
Hey, thanks, Carl. I want to thank you for a great introduction. I will be talking more about the sample prep approaches. One thing to consider before we actually get into the details is PFAS is a very unique compound. Again, as Carl has kind of indicated, it's pretty ubiquitous. It's found everywhere, and it does very well at what it's supposed to do. And one of its properties are that it's very, very resistant to degradation. These are forever chemicals. And as a result, they do tend to be very, very persistent. As Carl has indicated, they also travel very well within the ecosystem. They biomagnify. So you find them at increasing levels as you move up the food chain. All of these characteristics make the analysis of PFAS very important from the standpoint of health and safety, but it also makes it very difficult because they're very interesting from a sample prep perspective. The important thing to consider is right now with the PFAS analyses that are being prescribed or being done, the levels of detection are getting lower and lower. We're down into the single digit and sub-single digit PPT levels. Extremely small levels of compounds are being looked at. What that means is that you have any kind of interferences or any kind of compounds that can cause signals that are either enhanced or suppressed on the mass spec are going to cause problems with quantifying the amount of PFAS in your sample. In addition, these compounds tend to be very sticky. They stick to virtually everything, which makes it difficult to analyze, and also leads to a high degree of contamination, which Carl is going to touch on later on. They do also partition, especially long chain. The longer the chain, they tend to partition at the surface of the water, and then also stick to the surface of whatever vessel they're in, which again makes the analysis and the sample prep very, very difficult. Next slide, please. So PFAS, again, because it's found all over the planet, it's going to be found in a lot of different matrices. It's very mobile within the ecosystem. And because there's a couple of major sources, you're going to understand why you're looking at all these different matrices. Obviously, drinking water from a health and human health standpoint is the most important. And the primary source for getting the drinking water is through the water table, surface water, groundwater contamination, generally from military installations or firefighting installations. The 𝗣𝗙𝗃𝗃 or aqueous film forming foams that are used in fighting some of these jet fuel fires are made up of PFAS, and they will leach directly into the groundwater and then eventually get into our drinking water. But because these compounds tend to be very mobile and very persistent, they can go from the groundwater into a lot of other different environmental matrices. They're found in sediments, obviously in soils, and then of course, because they are biomagnified and they're very mobile within the ecosystem, they're found in biota, biosolids from treatment of water, as well as landfill leachates, because they're also consumer products. We use them, as Carl has indicated, in a lot of our products that we use daily, including microwave popcorn, for example, or Stainmaster for your carpets. So all of these industrial uses end up with a lot of PFAS compounds in our landfills, and then they'll leach out and then again get down into the water table, and you have this cycle beginning again. One important consideration is as these matrices get more and more complex, there's more potential for interferences with organic compounds that can cause enhancement or suppression of your PFAS analytes. And as you get more complex, you need a higher degree of cleanup, more manipulation of the sample itself to get a good quantifiable analysis. Next slide, please. So there's a whole lot of different PFAS methods, both a lot of them by matrix, as well as, of course, the different matrices. There's two official drinking water methods, EPA 537.1, which was promulgated back in 2018, EPA 533, which is the brand new drinking water method, which will kind of discriminate or contrast these in a few moments. And then you have other water methods that are not official prescriptive methods for drinking water per se, but they are used for wastewater, groundwater, surface water, other water matrices. These are both EPA derived as well as ASTM derived. You have a bunch of soil methods, which we will be kind of talking about. There's a food method that uses QueChERS and anion exchange resin. And there's now methods that are being developed and validated for other matrices, biological matrices, including serum, which is a very important consideration as we do more toxicology work and identify which of these compounds are bad or which of these compounds are worse, I guess you could say. Next slide. The other way. There we go. One important consideration that I do want to mention, there are a lot of different methods and a lot of different sample prep treatments for PFAS compounds or PFAS samples. What we're finding, though, is as these methods evolve, we're seeing more and more trending towards a wax solid phase extraction process. And I'll go into that in more detail, but that tends to be now becoming more standardized. The EPA has released a new draft method 1633 for non-drinking water matrices, which is not going to be discussed in detail during this presentation, but we certainly can go into this later on. But that also, again, for soils and other water sources and biota, now uses a wax SPE as a standard extraction mechanism. But getting directly into 537 and 533, so these differ by about 1 year of official release, but in reality, 537 was an older method. It was released in 2008 in support of the UCMR3 study on drinking water in the United States, and was revised in 2018 with a slight change of the mobile phase, or more so in the analytes and the solid phase extraction sorbent required. But then in 2019, when 533 was promulgated, the changes were much more significant. There was a change from 18 analytes in 537.1 to 25 analytes in 533. And this included removing 4 analytes from the 537.1 panel. And these were generally the long chain analytes. And in speaking to the EPA, there was a specific reason for this, because between 2008 and 2019, every single study that had been done on these compounds were showing non-detects. So it was decided in 2019 to remove these compounds from the PFAS analyte list, just simply because they weren't being seen. And in addition, they added 11 compounds, primarily short chain, and a lot of the compounds that are considered precursors. These are the fluoroethers and the fluorotelomere sulfonates that you can see here, that are all precursors and turn into, during oxidation in the environment, they'll turn into full-fledged PFOS, PFOA type of PFAS compounds. Next slide. So specifically getting into down to the weeds, what's really new in 533? Well, we mentioned obviously a whole bunch of new analytes. And as a result of these new analytes, there's going to be some changes to both the solid phase extraction as well as the diluent and injection solvents. The biggest change, though, is that 533 uses an isotope dilution process for quantifying the analytes. It allows the analyst to get a more accurate measure of the effect of the extraction and the sample prep on the analytes that are being looked for. And it allows you to get a more accurate and more sensitive method of detection and quantification versus just using internal standards. Another interesting difference here is the biocomposition. In 537.1, it was a 96% methanol, 4% water diluent or final injection volume or solvent. This is because the 96% methanol was required to solubilize some of these long chain compounds that were part of the 537 process. In 533, because now the emphasis is on short chains, which tend to be more soluble, you can use an 80-20 methanol water mix for your injection, which actually gives better peak shape, especially for the early eluting compounds like PFBA, PFBS. Another important consideration is the 533 specified that the sample volume and the sorbent mass in the SPE tube have a fixed ratio of at least 2:1. So for every 1 mil of sample volume, you need 2 milligrams of sorbent mass. For example, for a 100 milliliter sample, you'll need a 200 milligram SPE sorbent mass to extract this sample. For the 250 mil, you need 500 milligram sorbent mass. Another important consideration, really more for the commercial laboratories, is that 𝗔𝗻𝗃 was not required as part of the initial sample prep. So this was added to the sampling bottle during the initial sampling, and it just made it more difficult to get good, accurate, robust sampling. So now there's no 𝗔𝗻𝗃 added. Instead, they use ammonium acetate. Next slide, please. This is kind of a schematic of a typical SPE setup. This is a manual, generally a 24-position solid phase extraction manifold. This includes transfer lines from the bottle. You can see in this schematic that you have a transfer line going directly into the tube. Generally, with these type of systems, you're using a large reservoir, as you see number 2 in the schematic, a 60 mil reservoir that you then have the transfer line from your sample bottle going directly into. It allows for faster loading and less manual. You don't have to have an analyst standing there watching this the entire time. One important consideration is these SPE manifolds are sources of contamination. Carl's going to touch more upon this later. EPA 1633 actually requires a sodium hydroxide wash of every component of the SPE manifold, including those that are not in the flow path. And I know that there are some commercial laboratories that have actually taken steps to make the stopcocks and the needles going through the manifold to be completely consumable. So they throw them away after every single extraction to prevent any considerable or any contamination from the previous extractions. And this is why also that you see these dedicated to PFAS. You don't want to do other type of sample analysis or sample prep on these manifolds because of the possibility of contamination. Next slide, please. So going back to 537, here's a diagram of the sample prep steps. The biggest consideration here is that this uses an SDBL resin, a reverse phase polymer. Interesting story, in the original 537 back in 2008, it basically said a polymer. So a lot of laboratories kind of interpreted that as some of the new copolymers like 𝗪𝗏𝑋, which is a derivatized SDBL. But in 2018, the EPA actually revised 537 and emphasized that you cannot use a polymer. This is the first time I've seen this language where it literally said polymers are not allowed. You have to use, or copolymers are not allowed. You have to use SDBL only, which was a very interesting statement. So this obviously uses no buffer. It doesn't use any salts. It's just a reverse phase extraction. It's very simple. And of course, you see at the bottom that you have that 96.4 methanol water final volume, final solvent for your injection. And one important consideration also is polypropylene vials. This is required in all PFAS analysis. PFAS will stick very strongly to glass. Polypropylene less so. It does bind still, but it's a much weaker bond, and it can be disrupted with a high level of organic solvent, which is why all these, when you see that bottle rinsate, that's all going to be methanol that you have to use to rinse the bottle after pouring the sample into the extraction tubes. Next slide, please. And again, here's a schematic or a diagram of the process for the extraction of the 533 method. Again, because it's an isotope dilution method, you're adding your isotopes, your labeled analogs before extraction, because you're looking to see what impact the extraction has on the recovery of your native compounds. And this allows you to normalize that. What is not listed here is the conditioning step, which uses a buffer, a salt, to activate the ion exchange sites. So it's a little more complicated. There's a few more steps than you have in the reverse phase extraction that you saw for 537. You also have an elution with a 2% sodium hydroxide in methanol. So that disrupts the ion exchange interaction between these acids, the sulfonates and the carboxylates, with the ion exchange sites. And then the final volume or the final solvent is 80-20 methanol, which again is better for most of your peak shapes. Next slide, please. A few of the methods don't use extraction at all. They're direct inject, dilute and direct inject method. These are primarily ASTM methods. They are very rapid. They're fast and easy. Obviously, there's less sample manipulation. And they're used in a lot of laboratories as kind of screening methods to detect whether we have some of these PFAS that we then need to do targeted low detection level screening. One important consideration of these direct inject methods, they do work, but they do require a very sensitive instrument to get the levels of detection necessary to meet some of the criteria for the sensitivity that we're looking for. In addition, because you're not removing interferences, which is one of the major benefits of the SPE step, you have to have longer run times to make sure that you chromatographically resolve these interferences out, or you can see suppression of some of the quantitation, some of the levels of your analytes. Next slide, please. Soil is a very interesting matrix. There's a lot of work being done on soils now. As I mentioned, the new 1633 is fundamentally a non-drinking water method. And soil is one of the major matrices which is the focus of these methods. The reason being, again, especially around military bases, you get a high degree of contamination of the soil from the use of the AFFF in firefighting projects, whether it's training or whether it's actual fires. All that firefighting foam will go directly from the concrete down into the soil, and it contaminates the soil in the surrounding communities, especially. So what you found here is, I think there's 9 or 10 different soil methods. One important consideration here is very few of them actually use solid phase extraction. Most of them are just using either a dilute after a methanol shake, or they use a carbon cleanup to remove organic interferences, which can cause suppression of your PFOS primarily. You'll see that there's been some evolution of these methods as we move on. One other important consideration is, because of the methanol extraction, the initial methanol shake to get the PFAS off of the soil or out of the soil, you have a very high RSD level. It's about 30% reproducibility or RSD, which implies that these are not very robust type of methods. And again, 1633 has been designed to kind of address this concern. Next slide, please. Similar to what we've seen, this is a diagram or a flow chart of the general extraction mechanism for soils. You have this 1 hour long methanol shake to disrupt the PFAS, because it does, again, it sticks to the soil particles. It also tends to bind to the organic media, specifically long chain binds to the proteins, any proteins that are found in the matrix. So you have to spend a long time getting these compounds off of and out of the soil. So there's a long process of involved. Again, you see that these are generally transferred directly to the autosampler vial. 1633 does have an SPE step following this methanol extraction, which will concentrate down 250 times, making it a more sensitive assay, as well as removing a lot of the interferences that are found in the soil. Next slide, please. As I mentioned, that methanol extract does disrupt a lot of the interactions between the PFAS analytes and the soil, but this is not a very efficient mechanism, especially as the chains get longer and you get greater degrees of interaction with the proteins in the soil, in the organic media. You'll see that you need a higher number of extractions to get a full percentage, the 100% of the actual PFAS that's in the soil out of the soil and into your injection volume. ASTM method only uses 1 round of extraction, which is one of the reasons that the EPA and most of the commercial labs have probably not taken this method and made it a commercial product. Next slide, please. This is one of our partners. CEM has designed a new system, an automated system for doing that initial soil extraction, the one that takes an hour and results in sometimes you have to do multiple methanol shakes to get an efficient and high level of recovery of your analytes. This is just a very efficient and time a better use of your time. It provides a much faster and much more per sample, just a much better way of doing that initial extraction. And the more details are available on this system if you guys are interested. Next slide. So another matrix. This is getting kind of fun. Food is now a much bigger emphasis, actually much more so in Europe than in the United States. We're starting to see a lot of work being done on food, but nothing has really been promulgated, and none of the food companies are really doing this as a standard method. This uses a very unique process. It uses a QueChERS, which is a salt enhanced partitioning, liquid partitioning, to isolate the samples. And it's generally a kind of like the soil, use the methanol shakeout to get the PFAS out of the matrix without concentrating it. That's what QueChERS is doing in a food matrix. It essentially removes the QueChERS from the food matrix, but you still have a relatively dilute sample. So the FDA method for food does an initial screening after the QueChERS cleanup. And if you get a hit, if you get any kind of positive detect, you have to then do a solid phase extraction with wax with the ion exchange resin to further concentrate and remove any potential interferences, so you get an accurate and a lower level of detection for these analytes. Next, please. Again, here's our diagram showing the steps involved in this. One important consideration that is not listed on the slide is there's a lot of different QueChERS kits. We specifically, Phenomenex makes 6 different QueChERS kits with different salt levels, different buffers, different resins for either reverse phase or ion exchange resins and carbon, depending on the nature of the product to be cleaned up. So depending on the amount of fat or oil or the amount of pigment within the raw material, you have to use a different QueChERS mix to do your initial cleanup. Next slide, please. I actually had argued to remove this slide, but we decided to include it so you can kind of see what a QueChERS extract looks like. They're not really pretty, but again, you're kind of seeing the end product, and probably the most easy to see is the fish on the far right. Very messy sample, but you'll see this partitioning. You have your aqueous partition at the top, which contains your PFAS. You have your actual plug of material, in this case, the fish. You have your organic with the salt, your water with the salt below, and then excess salt down at the bottom. And the supernatant at the top, which is your organic containing your PFAS compounds, is the only thing you draw off and then use for your analysis. Next slide, please. Coming to the end, folks, we're talking about serum. Similar to food, we're starting to see more and more work with PFAS and serum as more studies are done in the toxicology and epidemiology branches of our science. We're identifying the problems with these compounds. We know they're in the water, we know they're in the soil, we know they're in our food, but one of the missing components is the actual physical biological impact that these compounds have on living systems. So as more and more studies are being done on PFAS within organisms and within serum, more work has to be done to get these efficiently and effectively out of that matrix and into an analysis, so you're getting an accurate and quantifiable level of actual PFAS. In the serum approach, you're generally having to crash out your proteins first, and then you have to do either a cleanup or an analysis. This can be done either manually, in the case of what we see in the schematic, where you do it in a tube with 50 microliters of serum and then 450 microliters of cold acetonitrile. You vortex it, you spin it down, you decant it, and then you extract again to concentrate and remove interferences that might have been still in your initial acetonitrile crash. This can also be automated. Next slide, please. This is a semi-automated version of the protein crash. Instead of doing it in a tube, you do it in a 96-well plate. It can be done, obviously, in a much more rapid fashion. And what we've shown here is the Preston positive pressure manifold, which can also help with these 96-well plates, because they can be done on a negative vacuum manifold, or they can be done on a positive pressure. The positive pressure provides more consistent flow because you're not drawing across a negative pressure across a large plate in which the vacuum tends to be kind of a gradient from one side of the manifold to the other. Here you have a consistent pressure being applied across all the plates or across all the wells, so you get very consistent flow. Next slide, please. The one important consideration for the serum analysis or the serum sample prep is these are generally very, very small samples. As we indicated earlier, it's like 45 to 50 microliters of total sample. You really can't do a good solid phase extraction using a tube. There's just too much sorbent and not enough sample to justify that. So we've designed a couple different ways of doing this. There is an automated version where you can actually do it online. As you can see the schematic here, this is a great way of doing it from a productivity standpoint. The only problems are that it requires a significant retubing. You have to use a very complex system of valves and software to arrange the flow paths. And you also have to clean off this cartridge relatively frequently because it's going to get junked up with some of these interferences and extraneous compounds, which you're planning on extracting out anyway. There's also a 96 well plate version similar to the extraction, which is not shown, which offers similar benefits to this online in that it's much more productive. But obviously there's certain benefits to doing it online in that you don't have these additional manual steps. And I think that will do it. I'm going to hand it over to Karl to talk about some of these contamination sources and how you can avoid and then mitigate them. Karl?
Awesome. Thanks so much, Sam. So when we were talking about setting up this series, and actually right before that, one of my colleagues, Craig, who will be leading the next session, asked me, what is the most common question you get asked about when it comes to PFAS analysis? And I think without a doubt, it involves contamination, questions about either they have contamination or they're looking to avoid contamination. So we thought this would be a great section to kind of dive into some of the things we've learned in the field and some of the things that we think you might want to look out for in your own labs. So we talked about some of the properties of PFAS, mainly it being non-stick. And when we think of things that are non-stick, well, that's a great thing to have in the lab, right? We don't want our contaminants sticking or what our analytes sticking to our tubing, et cetera. But it becomes a little bit tricky when we're trying to analyze PFAS, and the properties sometimes that make those things non-stick are in fact PFAS compounds. And if we take a look in the lab, some of the things we might find that may contain PFAS would be our tubing, auto sampler caps, a lot of times are PTFE, same with some filters are PTFE, some of the pipette tips, and I saw that question in the chat, some of the pipette tips, yeah, some of the low binding models can actually contain PFAS compounds. Along with mobile phases, your modifiers, all of those things might be contaminated with PFAS. So some of the things that we've personally found that work really well are the BD Falcon 15 mil and 50 mil tubes. So we've had really good luck with those. For pipette tips, Eppendorf and VWR are the two that we use in my lab, and we've had really great luck with. But overall, if you are unsure about a plastic sort of composition, or you're worried about something might be being contaminated with PFAS, the rule of thumb is just to go ahead and rinse it with methanol, do it 3 times. You can even add a little bit of formic acid, 0.1% formic acid, and that should help sort of remove some of those potential contaminants that might be there. So if we take a look at our LC system, so I have an Exion 2.0 LC system. A lot of questions I'll get are around the PFAS kit. What does it mean to get your LC PFAS ready? And what does that really look like? And if you have just very basic LC experience and you've done just basic LC maintenance in the past, you should have no problem installing one of these kits, whether it be on one of our systems like the Exion systems, or if you have an Agilent or a Waters, the process is really the same. We're trying to eliminate tubing that may be contaminated with PFAS, or may contain PFAS is probably a better way to put it. So one of the things we'll do is, from our solvent bottles to our degasser and our pumps, we'll replace that tubing with this natural PEEK tubing. It's a little bit thicker, a little harder to kind of bend. So if you are the kind of person who likes a really neat LC with nice lines, you'll want to heat it up with a little bit of heat to get it to sort of comply to what you're trying to do to it. But if you're someone maybe even like me who doesn't mind a messy LC, you can just go ahead and plug it right in. Same thing for some of the smaller diameter tubing. So those green PEEK tubing is what we'd use. And then probably the question I get asked the most when it contains or involves this PFAS kit is, where does that delay column go? And we'll talk about what a delay column is and its purpose, but where that delay column would go, which is circled in that light blue, it's right after your mixer. So again, that's where it is on this system. But if you have a different system, you just want to keep it right after your mixer. So where your mobile phase A, your mobile phase B meet, right after that point is where you would put your delay column. And just another example here of our previous Exxion system. We're just replacing this tubing. So we have the tubing going from the solvent bottles into our degasser, into our pumps. And that's really the main portion of the PFAS kit that you'll be exchanging regardless of your LC. So I talked about it, and I get asked a lot about it. What is a delay column? Why do you use them? And the delay column solves a really common problem. And its real purpose is to prevent the contamination from your LC, prevent that from coming out right on top of your peak of interest. So what this delay column is doing is, if we think about, we have two mobile phases, and in those mobile phases, maybe one of our solvents or our modifiers had some PFAS compound in them. And while our LC is sitting and equilibrating and we're doing our sample prep, or we are just loading our samples in, all of that contamination is starting to build up on our analytical column if we didn't have a delay column. So it would start to build up and build up and build up. And then once we do our first injection and run our gradient, all of that contamination is going to come off, and it's going to elute right on top of our peak of interest. And that's something we really don't want to happen. So what the delay column is doing is it's allowing the contamination to first build up on that delay column. It has to then travel through the delay column before ever making it to the analytical column. So it's holding up or delaying what your contaminant might be. So here's an example. We have our peak of interest. So we have a PFBS peak, for example, and that giant nasty hump that's eluting right after our nice peak would be our contamination. So you could imagine, if we weren't using a delay column, that PFBS peak would be right on top of our contamination peak, causing not a nice Gaussian looking peak, but also as you would run through your run, that contamination is going to change greatly depending on how long it was equilibrating and a variety of factors. So using a delay column is really, it's necessary. It's something you have to do for PFAS analysis, or at least something you really should do for due diligence. And these columns are usually just a larger diameter column that don't add a lot of back pressure to your system. So typically something like a 5 micrometer column is sufficient. So besides just contamination, the other issue that we face in the lab a lot is carryover. And carryover can be a little bit trickier, and it's going to depend a little bit based on what type of analysis you're doing. So for example, we might be having some ionic interactions with metallic materials. This is more of a problem if you're looking for methyl and ethyl fossa, which are known to be a little bit sticky with metal. There we can have some contaminant or some carryover issues. That's probably the two that I see more frequently. But you can also have interactions with your valve rotors, your fittings, your tubing, and it's going to depend a little bit on the classes of PFAS that you're looking at. Typically, to get away from having these issues, you can either lower your concentration. So lowering your concentration below 500 nanograms per milliliter usually is a good approach. But you could also maybe inject less. There are a few sort of key things that you can do to try to limit this. So the real way you're going to tell if the contamination or if the issue is contamination or if it's carryover, or at least figure out if it's past your autosampler, is whether or not it gets delayed by your delay column. So if you see it being delayed, that means it's upstream or maybe in your solvents, for example. And if you see it not being delayed, it's either from your sample prep or the autosampler. It has to be past that delay column. And that's usually a pretty good distinction. If you're running into these issues, one of the things I like to do is increase the rinsing. You can rinse with IPA and 50% methanol, or even adding a little bit of formic acid to your methanol usually makes a pretty big difference. And I just have an example here of where that carryover is sometimes coming from. So we've got our autosampler needle, and in the red, we have this little bit of side liquid that the autosampler needle is touching that really isn't being rinsed off. And the way we can kind of diagnose this is, do we see this consistent peak eluting at the same time as our actual sample? So is it being focused on our analytical column, or do we see this giant blob like we talked about earlier? And if this is what we're seeing, might be a chance that it's coming from our autosampler needle. To get rid of this, we can lower injection volume, and depending on your autosampler, you can actually go ahead and do some more external rinsing to try to remove this contamination, but it can be a tricky thing to do. So I've got a little bit of a case study here of a case where we had some PFBA issues. So I had a customer who was looking at their blanks, and all of a sudden they had this huge peak in the background for PFBA. So we ran a few blanks and we said, well, what could be causing this? Maybe it's just from the system. They had been running for a while. They didn't see this previously. So our first steps were kind of the standard steps. So let's make a fresh blank. Maybe something happened to your blank that's causing this sort of contamination issue. Maybe it was a dirty pipette, who knows? And that didn't fix the problem. So we said, okay, well, maybe it's something different. Maybe it's the methanol. Let's try a different methanol. That didn't seem to work either. Well, we then tried a different pipette. I've seen it in the past where certain pipettes can be contaminated with some sort of compound that looks similar to a PFAS compound. It's not necessarily PFBA, but it shares a transition or just increases the background. Maybe that's what's happening, but it wasn't. And then we tried a new column, also didn't work. So we finally rinsed the system with methanol and 1% formic acid. And what we saw was essentially no improvement. So we wanted to take a different approach, and we said, okay, well, let's look in our environment. So if we looked in our environment and thought, okay, where could this be coming from? It wasn't here before. Let's just do some simple methanol swipes around the room and see if we can try to narrow this down. So we took a methanol swipe of the prep room, saw a bigger peak, but still within the range of what we're seeing in the instrument room, just outside the lab. So actually in the break room, maybe somehow something's coming from there. Maybe they waxed the floors, for example, and it's causing our higher background. And then we just ran the same blank, and we saw, okay, well, that's not really where it's coming from. Let's continue on. And the customer at this point mentioned that, previously when I'd been there, it was extremely hot in this lab. They were using those small sort of window unit ACs. And they decided to switch over and get a mini split. But when they installed it, it was December. They didn't use it until recently. And that kind of threw on a light bulb for both of us. And we said, oh, we should definitely swipe that mini split. And what we saw was, yes, it was coming from the AC. So once they started using that AC, which was pretty much directly above the instrument almost, that's when we had this contamination issue start. And when we took a swab of the mini split, we saw, oh, yep, that's where it's coming from. So our solution in this case, we had to take apart the mini split and rinse it all with methanol, but it just kind of goes to show that, these contamination issues can be kind of complex, and it might not always be coming from the place you think it is. So you have to kind of think a little bit outside the box and remember that PFAS affects us or is used in a variety of products that we use throughout our life, not just in the lab. So with that, just thanks for being here. One of the things I just want to mention quickly is these PFAS regulations are going to continue to change. I mean, we have 1633, right? And as Sam went through, there's a variety of sample preps for different matrices. So it can be confusing. And it can be challenging because PFAS is essentially everywhere. So if you're having questions or you have any issues, please feel free to reach out to myself. Our application teams at SCIEX is wonderful, Phenomenex as well, because we all are affected by the PFAS, but it also affects us. A lot of us used to research it. And if there's one thing that researchers love talking about is research. So we'd love to talk to you about it more. And with that, I'll go ahead and open up the floor and see if anyone has any questions.
Thanks, Carl. As we get into the question, I'm just going to launch a little exit poll. There's just 2 questions, if you wouldn't mind taking a moment and just checking those boxes there. I appreciate that. Really great. I never would have expected it was the air conditioner. That type of detective work always makes me really happy to see. So yeah, we do have several questions. We have about 8 minutes left, so let's just plow in and see if we can't get through them. So the first one is for Carl. How did you collect the sample from the air conditioner? Could you be a little bit just more nuts and bolts, provide some specificity there?
Yeah, I can. Very simply, we just took a Kim wipe soaked in methanol and just wiped it on a variety of surfaces, and then squeezed it and took that methanol and put it in an autosampler vial. So nothing too fancy.
Bucket chemistry. All right.
Yep.
Great. So one more for Carl. Is there a solvent provider or type that you would prefer, something that you found is generally less of an issue for PFAS contamination?
Yeah, I get asked that quite a bit. And the first thing I would say is try to make sure that it's LCMS grade. That's very important. In particular, in our lab, we found that JT Baker usually has a very clean background. So that would be the one I usually recommend.
Okay, good. Sam, actually, sorry, one more for Carl. You kind of answered this, but should you avoid pipettes in sample, or have you looked at pipettes? Nicholas mentions that some have Teflon parts and some of the lubricants you might use in your pipette maintenance could contain PFAS.
Absolutely. Great question. And yes, typically we see the contamination coming from the tips more than the pipette itself. But you certainly want to make sure that you're using a tip. Again, I've had really great luck with epinephrine and VWR, but you want to make sure you're using a tip that doesn't say low binding, for example, on the box.
Gotcha. Okay. Sam, have you observed any PFAS contamination? Maybe this is a Carl question. I'll open it up to the floor. Have either of you ever observed any PFAS contamination from the phosphate salts used in the buffer for 533?
Carl, let me try this one starting at the beginning. Short answer, no. However, I think Carl has kind of indicated, and I hopefully touched on this a little bit also, these compounds are everywhere. And it's not a matter of if you're going to get contamination. It's really, truly a matter of when you're going to get contamination. We're initiating some QC steps that are going to batch test all of our consumable products for PFAS, and that's going to at least provide some confidence from the end user that the samples they're deriving from these consumables are going to be free of contamination. However, again, any of your solvents, any of your salts, any consumable can have PFAS contamination. And it gets even worse in that once I test it and I show that it's clean, it could be contaminated in transit. It could be contaminated, as Carl has kind of indicated, from some extraneous stuff that's happening within the lab or within the stockroom. So you really got to be aware of the possibility of it, and you should be doing lab lengths for every single product that you use in this testing to ensure that you are identifying any possible contamination. Karl, can you add to that?
Yeah, I would just agree. And sometimes you'll see contamination that appears to look like it's a PFAS containing compound, and it might be, but it might not be the analyte you're interested in. It might just be something else. So we used to see that with 𝗔𝗱𝗃 quite a bit, which made us have to change one of the transitions, and that eliminated the problem.
Yeah, and again, just to add to that again, is a lot of these compounds that are considered interferences, you really don't see them a lot of times chromatographically, or you may not see them when you're looking for targeted compounds, but they will affect the quantification of your analytes. They'll either enhance or suppress depending on which ion transition you're using. And yeah, in a lot of cases, the easiest solution is to make sure they're chromatographically resolved and or use a different transition ion to quantify, and that becomes less of an issue.
Yeah. Okay, we have quite a few questions here actually coming in, so let's jump through and see what we can get through here, guys. I guess this is a specific one. Maybe I'll direct it to Karl. Have you ever seen 6,2-FDS contamination? If so, how do you deal with it?
Yep, definitely have. And in the past, when I've seen it, it was from the SPE cartridges. And one time it was the sampling manifold, actually. So we ended up trying different SPE cartridges. A different batch actually solved the problem. It was a specific batch.
Going back to your first principles, right? Start eliminating variables and just work backwards logically through your prep flow. Okay, great.
Exactly.
Yep. There's a lot. So I believe that the EPA methods might specify the sampling containers that you use. Is that right, Sam?
Yeah, absolutely. They basically say do not use anything glass. All the sampling containers have to be polypropylene. All of your transfer lines and your vials have to be polypropylene. And again, you're going to get some non-specific binding of PFAS, even to polypropylene. It's a sticky compound. And again, as you increase chain length, it becomes even a worse problem. But with polypropylene, at least, you don't have the hydrophobic interaction. So you get less intense binding and it can be disrupted a lot more easily with organic solvents.
So you have some surface sorption to the glass, but the flip side is that you don't have any PFAS contamination from the glass. So you have differing problems to deal with. Right?
Exactly. It's kind of like for everything you do to mitigate the problem, you're in some cases adding other issues. So
yeah, sure.
It's kind of like a Jenga. You better be careful when you put that piece out.
Sorry, I'm just going through the other questions here. Karl, what kind of detection limits are used for instruments that measure PFAS directly in water? That's a little broad, but can you touch on that briefly?
Yeah, and it's going to vary quite a bit depending on what system you're using. Typically, we would be talking about in the parts per billion range. And then depending on your sample prep or the approach you take, if, for example, you wanted to do a large volume injection, you would be into the parts per trillion range.
I'm going to jump in on that also, Karl, because the issue here is really what the regulatory limit of detection or limit of quantification also is. We're seeing more and more sub-PPT requirements. So depending on the method you're using and the regulatory prescriptive requirements, you could be anywhere, as Karl said, from the part per billion to the sub-single digit part per trillion requirements, depending on the analyte and the matrix.
Great. So we're at the top of the hour here, folks. I know there are some questions that have been left unanswered. What we'll do is I will distribute those to the appropriate speaker, be it Karl or Sam, and we'll make sure that you get a response via email to those. Okay, everybody? Thank you so much for everyone who attended. Keep in mind, this is a 5-part series. The next one's coming up March 31st. So if you haven't already registered, come on over. It's all quant all the time, all about LCMS and how it can be used to quantitate these really fun and persistent and annoying compounds. So thanks again to our speakers, Karl and Sam, really great stuff. And everyone enjoy the rest of your day. Thank you for attending.
Thanks.